We've now got a talk on Phoebe the quadricopter from Andy Baker, and he's going to tell you a bit about how he's built it. He's not going to fly it actually in here today. We didn't want to have too many people.
And that is a serious risk.
Front row. However, he is going to take you out a little later in his talk to outside for those who actually want to see it fly.
And actually, I'll probably do that within the next 2 or 3 minutes, because once you've seen it fly, you'll think, it took him that long to get it to do just that? And then I can spend the last 20 minutes of the talk telling you why I don't have anything like the level of control I'd like to have. So yes, be prepared to be disappointed at the test flight. Put it like that. I'll set your expectations low, and then it can only get better. So, Phoebe. Just felt like giving her a name because I get fed up of calling her a quadricopter or a quadcopter. It's just too many syllables. There is to her not many bits, really. Most of this looks like off the shelf, but the yellow blob on the top, the yellow rectangle, cube, whatever on the top, is actually just a Raspberry Pi with a Pipo style case. It's a Model A Raspberry Pi. And then basically just a breadboard on top to sit a couple of sensors on. And the sensors are an accelerometer and a gyroscope, and that's it. The rest of the kit is basically just off the shelf for quadcopters, where people just buy them off the shelf and fly them around with remote controls. To give you a quick run through, so you might be aware of quadcopters, and they've become a lot of boys' toys kind of things, where you just go and buy them and fly them. That wasn't my incentive. I wanted to know how they worked. I started from complete, utter and total ignorance, and it's taken me about 18 months to get to the stage where I am. Some of it's my fault, and I'll try and explain that later on. If you haven't seen one, if you haven't flown one, or seen one on the TV or on YouTube or whatever, they're used quite a lot. If any of you watch Countryfile on Sunday on BBC One, whenever you see an overhead view of a presenter, or you see something skimming across a cornfield, it's a quadcopter. It's not a helicopter anymore. Countryfile definitely have their own quadcopter, and they've basically got a two-man team, one flying it and one controlling a camera that's slung underneath it. So keep an eye out for it. Certainly the one over the cornfield, you could actually see the shadow of the quadcopter moving along the right-hand side of the TV frame, but you just had to watch out for it. Yes, as I've already said, keep your expectations low. So Phoebe, no remote control. She's basically completely autonomous. She's got a flight plan programmed into the code. The flight plan is just a very simple 3 seconds takeoff, hover, and descend. What you expect from that would be, what you'll see will be quite different, and then I'll explain once we're all back in why that's the case. And as I say, stand well back, be ready to run. You shouldn't need to run. Basically, if you all hang out by the soldering tent outside, just beyond it, and I'll go up onto the level area there, and hopefully get it to perform in some level of behaviour that you think is cool rather than utterly crazy. Okay? Right, if you can head out to the soldering area. Oops, cheers, thanks. Yeah, anywhere there's just fine. It's just out of the way of the solderers, and I'm going up to the park bench up to the top. So she's already powered up. I've got a small battery at the end that's just powering the Raspberry Pi, and then I'll connect the big battery that's powering the motors and everything else once we're up there, because it's noisy, it's irritating. So like I said, she should just take off, hover and descend. That is not what she will do, I promise you. And so, right, are we in? Yep, she's alive. The only control I have over her is either start up the Python code. So basically all her code is written in Python, so all I can do is SSH into her. That's all I'm doing from my iPad. It's nothing special. I've just got a secure shell into her. I then start the Python code, and all I can do from that point onwards is hit Control C. So depending on what she does, she may then suddenly crash out from the sky and land hard, because when I see her drifting that way, too high or whatever, I'm just going to kill the flight. First thing though, put the main batteries in place to drive the motors. I'll explain what the noise is when we get back in. Okay, so that's the Python code just running. It's got a few, probably about 30 seconds of just testing various things, getting them running, checking the sensors, and also it gives me a period to panic and think, no, I got that wrong, hit Control C before she actually gets off the ground and starts being dangerous. 1 second or so to go. Hover for a few seconds. Oops, is she going to come down? No. There we go. That is actually about as good as it gets. And I'm almost tempted to not do it again, because it can only get worse from that point. I'll have one more go, see if I can show you how badly behaved she can be with an identical test run, and then we can all head back inside again. Oops. Fingers crossed. Oops, that doesn't sound good. That sounds like a loose cable somewhere. Oh. No, something got broken on that last crash landing, so I'm going to have to call it at a good flight and not demonstrate to you how bad she could be. Head on inside and I'll follow you in. Yeah, that actually.
There's been a few hard landings.
There's been a lot more. I have spent so much money on propeller blades. It's generally propeller blades that go, and it's because I started from complete ignorance. So, you know, a lot of it was. Sorry.
Put a guard on.
Yeah, but the trouble is actually a lot of the crashes come from angles like that, and they hit the ground hard, so even a guard that isn't strong enough, these aren't gentle nudges, these are high speed nudges. And you know, I've got cuts in coats, I've just slashed my kids' paddling pool open, their trampoline doesn't have a safety net around some parts of it anymore. There's just been, no, these things are just dangerous. No, one of the wires somewhere will have disconnected. So, but at least we got one test flight out of it, which is the main thing. The Raspberry Pi side of her is actually still alive, so that's why I recently swapped it to run off 2 batteries, because I used to start getting all sorts of problems from battery power running out for the main motors, and then the Raspberry Pi rebooting in mid-flight, and that obviously isn't a great thing for controlling flights. Now, do we have a... Seem to have... Oh, here we go. So, yeah, now we don't have the motors powered up, I can probably do another test run. Let's just reconnect while she's obviously lost a connection. Yeah. So that was all I was typing in as part of a test flight, or as part of the flight you saw. That first dump is a whole load of configuration parameters that I could tweak with while I was doing any testing. There's quite a lot of them. A lot of them are completely stapled, which is why I didn't have to type any of them in the command line. So that's probably one of the most important things. The last pitch is trying to actually measure gravity when she's sitting on unstable ground, and work out what the real gravity value should be when she's horizontal. So you can see various zeros and ones, and so the 0.99154 is kind of a measure of gravity on a tilt, and then it gets converted to 1.000 whatever to work out where gravity is, because she needs to know which way is up, and gravity is the only way that she can tell which way is up and which way is horizontal. Anyway, yeah, let's go on with the presentation side of things and see where we got to. Okay, keep your expectations low. That was actually quite a good flight. I don't know if you caught it, all of it. Something happened when she came down, and there's a wire loose somewhere, which is why she didn't stop beeping when I tried that second run. And that's why I wasn't willing to run the second run, because if she doesn't stop beeping, it means one of the main connections to the motors is not connected properly, and at that point the flight would have been, well, she'd have just broken. Basically, she'd have flipped over and hit her head. Right, quick run through the bits and pieces on the hardware side. Propellers, motors. The first thing of vague interest are these things called ESCs, electronic speed controllers, which they actually aren't. They're kind of they're a converter that takes a PWM pulse width modulation signal in, and out goes, basically it's got a variety of H bridges, if you know what they are, inside, and it basically powers the motors according to whatever the PWM signal is doing. So there's a small microcontroller in there basically running that. You just buy them off the shelf and you just use them. Beyond that, what have we got? Raspberry Pi is actually doing everything else apart from that. So if you buy one of the ones off the wall, or if you're off the shelf, or if you go and look at most of the DIY ones, they've got Arduino kit running in there, and I really did not want to do, I wanted to make it as Pi unique as I could. I wanted to use as little of anything else that I could. I wanted it to be pure Python if I could, because I write C day in, day out for work, and I wanted to do something that had absolutely nothing to do with work. What else? Yeah, that pretty much sums up what's going on in the yellow cube, well, in the yellow rectangle. And yeah, it took me a while, but now the only thing that is not run on the Raspberry Pi are the actual sensors themselves. So there's a small sensor breakout on the top, so the whole breadboard is essentially mostly just wires connecting things together. The only thing of any significance is the sensor that's in the middle of the dome and the 4 wires that are connecting the PWM signals out to the motors. Right, wake up you, it's not that boring. Wrong way. There we go, tell who wasn't concentrating enough. Yeah, and the whole thing, other than the frame, is actually just a combination of Velcro, blue tack, and double-sided sticky tape to stick it together, simply because then when you crash, it's easy to disassemble everything and rebuild it from scratch. So yes. Software, I'm not going to go through the software in a whole lot of detail because it's tedious and I'll say something wrong and then you'll laugh. This is kind of a diagram of how all the bits glue together to keep her roughly horizontal, roughly not drifting left-right. The round circles are a representation of what are called PIDs, and they basically take an input, so what the sensors are reading, a target, which is what you want it to do, and with some relatively simple, well, in fact very simple maths, put out an output, which is what you want the motors to do as a result. So they don't, and basically it uses a feedback mechanism. In this horizontal case, there are two. There's one on the right-hand side that just stops, has stability, so she doesn't jiggle, she doesn't flip over her head. And then the one in the middle is to do with velocities, so that in this particular case, the 3 steps of the flight plan are rise at 0.3 meters a second for 3 seconds, stay where you are, no movement on any of the left, right and up frames for 3 seconds, and then descend for 3 seconds. So that middle one, the middle circle, is basically controlling speeds and then putting output into the right-hand circle to say, right, okay, this is what I want you to do to correct my speed errors, and then the one on the right-hand side controls stable rolling in directions to basically control what speed she's drifting left and right. So I don't know whether you saw, she did drift a bit. She did also try and then correct it. So she started doing like this and then she swung back slowly, but at the same time there's underlying drifts that she doesn't try and correct.
None of that's analog, that's all...
That's all, so yeah, so the sensors, everything along the top of the diagram, basically where I'm mentioning angles or acceleration, all that. So that all comes from the sensor unit that's on the breadboard at the top. The actual sensors are analog, but inside the thing, then there's 2A to D converters and whatever, so that it's basically what the Raspberry Pi gets is an I2C connection to get the actual data. So you've got about 2 bytes of data for every sensor. So there's about 6 sensors. Well, there are 6 sensors in there for X.
You've implemented the actual control system itself down at the bottom there. You've implemented that. That
whole, basically every part of that is written in Python, and we could go through the code, and you could get very bored because it's not that interesting. But my aim was to get it done in Python, and the key bit there is primarily performance. It's getting Python to run fast enough, and all the components to run fast enough to actually make it achievable.
What sort of update rate are you getting out?
So I am getting, the code runs at about 450 loops a second, and each loop, have I got a loop?
Oh, sorry.
No, I don't think I was trying to avoid going through a loop, but essentially that diagram is a loop. So each one of the loops of the code, 450 times a second, reads all of the sensors and basically just averages them, or in fact it's integrating them because it's multiplying them by the time period since the last sensor read.
Can you give us a description of the notation that you're using? Is that theta?
So yeah, let's go, I'll happily do that. So basically for the angles, I'm using the angle of, it's a theta and it's an angle of tilt, and you're measuring that angle of tilt. You measure it in 2 different ways. The gyroscope, you're basically sort of integrating, so that's what the sigma gyro delta t is there for. It's essentially it's integrating, but what it's actually doing is just 400 times a second reading the sensors, multiplying by the amount of time since it last read the sensor, and adding it onto a...
So T is going to be time, what's D?
It's actually dt, which is the delta in time. So, so it's the time since you read the sensor last time. So each time you read the sensor, you take a timestamp, and then when you read it next time, then you basically multiply those together, the timestamp times where it is now, and that basically converts a gyro output, which is a rotation speed, into an actual angle that has changed since the last time you looked at it. So you're constantly integrating the gyro output to come up with an angle.
The gyro T, delta T is always dynamic.
Yes, yeah. And likewise, the accelerometer one, so when you've got the accelerometer, that's measuring acceleration, gravity plus any movement left, right, up or down. And if you don't have any acceleration other than gravity, then you can run the X, Y, and Z axes and use whoops, sorry folks, use a Euler angle calculation that basically churns out the angle of tilt in the same way that the gyro does. The difference is the gyro is good short term, but because you're integrating and you're not actually integrating, you're adding up, it'll eventually drift out of accuracy. Long term, the accelerometer Euler angles are great, they're perfect, but short term, they're picking up all sorts of noise from the motors and the propellers, so you can't use them short term because they spike all over the place, but if you average them out long term, then they're good. So they go through this filter basically that merges the two, uses the gyro short term, uses the accelerometer long term, and then those angles are used for various things to basically either detect tilt, well, primarily to detect tilt, and therefore either decide whether that's the right level of tilt to correct something, or in fact whether that's a tilt that's an error and needs to be corrected in a different, by then triggering an output from the PID code. I don't want to go into the PID code anymore because there's a presentation this afternoon on PIDs and robots, and they'll probably know it an awful lot better than I do and be able to present it a lot better than I can.
Is that complementary filter, that's in the 6050?
No. The MPU 6050, which is the sensor unit, does come with a whole load of internal motion processing code. I didn't want to use that. I wanted to understand how it all worked. So there's an awful lot of stuff that I'm not using in that inertial motion unit, the IMU, that I could have done. But I wanted to learn how these things worked. I wanted to work it all out for myself. And I wanted to work in Python. So no, everything is in my code. All I'm reading is raw sensor data, and that's it. Which is why it took me a year and a half to get to this stage, because I was just going through complete ignorance and trying to work it out.
You must be adding to the weight quite considerably by using breadboard and various bits and pieces.
Yep.
What was your reasoning for doing that?
Initially, because it was a project under development, and if I soldered things on, I was bound to get things wrong because I didn't know what I was doing. And the breadboard.
Surely that turns past now, that maybe.
It is, and in fact I have another one underway with that's going to be based on a B+, simply because that's the smallest thing. Well, it's got the better power usage. It's got its own hat PCB that's going to be on there. I'll put the same circuit on there, but it'll be all soldered on. So yeah.
Broadcasting using the speaker, I guess.
Yeah. Right. I'm not sure how time's going. I've got a little bit. The main problem, so this is the key bit. Why did she drift? Why did she keep going up when she should have been descending? And it's a few months ago I would have said it was a bug in my code. Now I am pretty adamant that it is not, and that it's simply down to the sensors themselves. So critically, the accelerometer that's measuring how fast she's accelerating upwards and sideways has got about 1 or 2% accuracy, or critically 1 or 2% error in the accuracy. It also, that's as far as scaling is concerned, but it also can be offset by a certain amount as well, and there's about 1 or 2% error in that. And when you're using it to calculate the speed that she's moving, so she's sitting on the table like this, if the sensors are inaccurate, then the sensors may actually be feeding in that she's moving. And that's why you then start to get problems. So if she's, as I say, if she's sitting like that, but thinks she's moving, say forwards, then when she actually lifts into the air, she's going to try and compensate for that movement forwards that she perceives is going on, and she'll suddenly start dashing backwards. So I've gone through hoops to get the calibration as best I can by basically sticking the Raspberry Pi and the sensors into a clear cube, and you just kind of turn it around all 6 axes, read the measurements, try and average them out and whatever. What you saw is the best result of that, because also the readings drift by temperature. So I did that indoors yesterday. Today the temperature outside is different, so all of the calibration I did is now all slightly off, and what was yesterday a perfect flight, today has drifted. Getting towards the end, don't worry. So, yeah, you were asking about loop speeds and things like that. So the main, as I've said, the main loop runs around hard as fast as it can, just reading the sensors. I've decided arbitrarily that then, having averaged or integrated the sensors over, 400 times, 450 times a second, about every 40th of a second, I update the data to the motors, basically. Kind of figures that if you think she weighs 1.5 kilos as it is, she's only got props on the corners, she's not moved, she's wobbling like this. You don't really need updates of any real significance. And so essentially that gives me the possibility to average out the sensors and take out the noise that comes from the motors, the vibrations from the motors and the propellers, and just feed in, fingers crossed, more accurate values. When I started doing that probably a year ago, maybe more, I was only getting about 100 loops a second, and I've had to go through all sorts of bits and bobs just to get the timings up, and sometimes they've been quite amazing, the kind of speed advantages you can get. I think probably the best, looking at the list, was actually calling time.time. So you need to know the time that you read the sensors. And I'd got other places I needed in the code to know the time. And previously I was just calling time lots of different times wherever I needed to know it. If I called it just once at the top of each loop, and then just use that value everywhere else in the code, that actually more than doubles the speed. So there's an irony that actually finding out your time takes more time than you actually want it to do. The rest are all just bits and bobs. But yeah, I got it from probably 100 hertz, time.time doubled it up to 200. Some data reading probably took a lot off. The next most significant one was I ended up I rewrote a little bit of the GPIO code to speed that up to be able to catch data as soon as it was available, rather than having to wait for it by just sitting spinning. So what next? Yeah, I've already mentioned I'm going to rebuild the body, use a B+ Raspberry Pi. I'm going to change it to a PCB so it's more solid, because basically when she hits the ground, wires tend to fall out, and that was probably what had happened on that second flight just then. More to the future, though, is to get those sensors better. I can't do a great deal about the gyro and the accelerometer. They are just about as good as they come. I can sort out the height with a barometer, which is basically just measuring the air pressure, and you can get ones that are fine enough to read basically air pressure differences over, say, 10 centimeters, so that if you want to rise to a height of 1 meter, you're going to get just a 10% error on that. So that would be better for vertical climb speeds. I really have no idea what I can do about horizontal. The only real, because you need to have real motion detection, about the only option, you can either buy off the shelf ones, but they're about 100 quid, which is way too more than I want. And anyway, I'd rather do it by myself if there's a way. The other way is to use the Raspberry Cam to take videos of the floor that she's flying over. And part of the graphics processing to get one frame in a video to the next one is to actually know which way one frame of a video has moved to generate the next one. And out of the GPU on the Raspberry Pi comes a whole bunch of vectors that say this frame moved this direction to go to the next frame. And that information could then be used as a motion tracking system, so that as you're videoing the grass that she's flying over, she could detect, the GPU could detect changes in the picture that the video is taking, and therefore see that it's moving that way.
Is the grass rather uniform though?
Depends on the resolution of your video, doesn't it? I don't know, I haven't tried this. This is just my speculation at the moment. I'm hoping grass is suitable. Sorry? Yeah, and we do have a lot of weeds at home, so actually it'd be all right. Yeah, the only other things I can do, by adding a magnetometer compass, I'll have a much better idea of where she's pointing. So at the moment, I've got a bit of code that stops her rotating around. So it's yaw is the name of the rotation, but there's a bit of code preventing the yaw, which means that she keeps pointing the same direction, and I just don't worry about it for the moment. But if you add a compass, then you could make her deliberately turn where you want her to go.
You said you were getting a lot of noise on the sensors. Have you tried like mechanically dampening the sensors so they don't pick up?
Yep.
Oh, okay.
Yep. So what have we got? We've got the yellow box is double-sided foam sticky taped onto the main frame. The breadboard is then on rubber standoffs onto the Raspberry Pi, so there's a double level of physical separation. But I think fundamentally, probably doesn't help that the motors are there and the main noise is going to be coming from the propellers, and the sensor is at exactly that height. But that was just I ran out of, there's no space underneath because that's stuffed full of batteries. I didn't want it anywhere down here because of the way she crashes hard down onto the ground, so that was the best I could do. And that's part of the reason actually for getting her onto a B+, because I can get the circuitry down inside the case, I can get it below the main blades, the main propeller blades, and therefore reduce the, hopefully reduce the noise levels as well. But I think by using the averaging and only feeding the motors by every, a tenth of the number of samples, that had the biggest improvement. And my main problem now is simply that the sensors are not accurate enough.
Surely it's electrical noise that you must suffer with, not audible noise.
Now that would be the case until a few months ago. So yes, electrical noise, I actually had problems with her dropping out the sky, because if there was a sudden change, you'd get a huge current boost from the big lithium battery there. The voltage drop from that would then not be enough to power the Pi, and she'd reboot. And yes, there was electrical noise as well driving the sensors. I had got a regulator in there, but not enough. Which is why now there's the big power one there, but there's also a little phone charger battery there running quite independently and hopefully noise-free, because it's just it's just another phone charger job. And life has been an awful lot better since I've done that. So.
I was going to say, if you're reading these sensors, you know, as you read them faster, the actual noise increases.
Yes, the actual. I think the way the chip works. Obviously, it's an analog to digital converter. I think the conversion speed, the rate of the actual converter, is fixed, and then you can sample the data from that at a given rate. And so, and then there are internal filters, digital filters, to actually limit noise from that. So I'm pulling data off the sensors at about kilohertz, so faster than my code can run.
You have to use analog to digital, why not digital to digital?
I don't use analog to digital, but it's the chip itself that I think the actual sensors are analog. Well, they are. So it then basically uses a 16-bit analog to digital in all 6 axes, essentially, 3 for the gyro and 3 for the accelerometer. Are you logging any of the data? Yes, certainly when I was doing until testing very recently, and I'm talking a week or few ago, yes, I was logging absolutely everything. So not only the data, but the interpretation of the code at every step along its operation. That slows her loop speed down from about 440 to about 390 something. So she's still flyable at that. The only problem it gives is you read a whole bunch of sensors, you sort them out, you've passed them out to the motors, and then you write the logs. And in writing the logs, that takes time, and it makes it just ever so slightly more unstable. I've done things like, so the logs are written to shared memory and only dumped at the end of flight, so you get fast writing to a shared memory file. I've locked her code in so that she can't be shared, sent to disk and then dragged back from disk. The code is permanently locked in memory, and it's all right, it's good enough. I'm getting to the point where I can't use the diagnostics anymore because they affect, it's the Schrodinger's cat thing. If I look at the diagnostics, then it changes the way she flies. So it's getting to the point where it's gut feel and, guesswork, gut feel and guesswork. Try some. Sorry? No. No, it's simply because 10% is neither here nor there. I've gained 400% by just fixing the code. So.
I found the Pi does take really well to overclock it.
Does it?
You can some of the ones, the memory ones, you can double quite easily, and it still runs fine. So
right. What's the memory one?
It kind of runs at 750 megahertz as standard, as bog standard, and you can certainly take it up to close to 1 gig.
Right.
I think I'm running
That's like more than 10%.
Yeah,
it is. I'll give you that. Yes.
Yeah,
it's more like 30, isn't it?
500, I think. Is it a common one? Something like that. But I've not had a Pi crash yet from doing it. So
really? I have.
Yeah.
not from doing that, but.
The only issues that I've heard about that result from running it at, I think the maximum is about 950 meg.
Right.
Is that it somehow affects the SD card.
Right.
I'm not so sure if that's true on the B+.
Yeah, that's when I found the thing that's going to fail first when you're overclocking is the SD card. So if
right.
you're running all in memory, you'll probably be fine. If you're trying to log data.
Well, the log only happens at the end of the flight anyway. So either when I hit Control C, or a flight ends in a nice way. Sorry.
That would limit your flight time. Because you're logging it all into memory and then doing the dump.
It does, but at the moment, as you've seen from the test flight, a 10-second flight is perfectly long to see errors and work out what's going on. And I've reached the stage now. Yes, loop. Yeah, and it's kind of like it's
not long.
No, but until I can work out ways to improve or to replace the accelerometer as my main motion controller, I don't think anything more than 10-second flight is actually viable. I could try. Well, there are better ways I can do calibration, and I've done it before, but I ran out of time for this presentation to actually do it. So I could probably get it a little bit better, but I've got no insight. My aim was not to produce a toy to play like that. My aim was to understand how these things work. So even if I don't actually ever get it to be any better than it is, it's still a success as far as I'm concerned, because I know what's going on.
Are you planning on this being autonomous all the time?
Yes. Right. This was purely a project. Okay, to give you how are we doing for time? Is that orange? Which means?
I've got about 5 minutes.
That's fine. So, like I said, I started from complete ignorance. I thought that autonomous was an easy step to go before you then add a joystick and a human being on the end. I got it completely the wrong way around, and I only actually realised that a couple of months ago. So if you buy them off the shelf, the set of PIDs that you've got set up are completely different. You'll still have the one on the right-hand side. You still need stability, so that when it's been told to go to a given angle, it stays there. The difference is that one in the middle, I've got that based on on speed. So it's detecting speed and trying to undo any speed that is not part of the target. So if you're aiming at hover stable, any speed it detects that way, it needs to tilt that way to get it back where it's going. The ones off the shelf don't have that. They're just based on angles. So you basically, the remote control is setting angles. So that middle one is basically you're just saying, I'd like you, as you push the joysticks around, it's saying I'd like you to tilt at that angle, and that will slowly accelerate it into a direction you're going. And then as you change the remote control and fiddle with the joysticks, it goes around like that. And so basically, the person doing the horizontal speed PID is a human being in the feedback loop of actually watching the quadcopter fly, spotting the feedback against what it actually wants to do, and tweaking the joysticks to actually make it work. I thought that would be hard. And so I thought, I know, I'll put motion control in there instead. And that's why, well, I went from complete ignorance. I've been honest. Sorry? And actually, again, that Python I knew wasn't an ignorant decision. I knew it would be a challenge, and that's why I did it. And actually, Python is working well enough. The sensors are, the code is fast enough. It's simply I'm now down to the accuracy of the sensors, and probably my next step is to try and get my best calibration possible, which involves, as I say, this clear Perspex cube that I glue the Raspberry Pi or use double-sided sticky tape to stick her inside, and then I can rotate her around her axes and measure the offsets and gains in the sensors. And a beer fridge, because then I can do that at a known temperature, and then I can do it at, say, a room temperature or a nice warm temperature, and then the errors in the sensors are approximately linear, so that you can calibrate, so that basically as she runs, she can calibrate the accurate values for the sensors based upon the current temperature, which she can read anyway, and then apply the maths to basically come to this, to come up with whatever the accurate values of the errors are.
So by the sense of it, what you want is a table of... because it's linear, you can actually do it as just an equation. And in fact, I've done it before in the past, but I wasn't careful enough in doing it.
Is there a way to have sort of self-calibration, or do you need GPS for that or something?
I have actually got some self-calibration, but it's sort of, if she's, well, you'll have to imagine, because of the rubber ball, she's leaning on the table. And what you're trying to do is you've got the only force on her like that before takeoff is gravity. So you can't do an exact gravity. Can you do an exact gravity measurement? Because of the offset in the sensors, you can't just say, well, the vertical measurement I've got is gravity, and because of the tilt she's at, you can't say the vertical offset she's got is gravity. You need to account for the angle, which you can only obtain from the accelerometer, so you're using known flawed values to read a better value. So I've had to go at kind of iterating around that to get the angles better and then read gravity better. And actually she's running that code during that test, so it was an iterative gravity calculation. And it improved things, but at the amount I'm using that acceleration, I need the accelerometer, I need it to be as accurate as possible. And
The only thing I'm thinking is
very complementary filters to check the possibilities on that to see if some of the errors are being injected from the filters.
that is, yes, you're absolutely right. I have there's both complementary filters, which are filtering out noise from the angles. There's also filters within the sensors themselves that filter the raw data from the sensors. And yeah, an awful lot of my testing has been, essentially juggling the sensor outputs and the filters that are being applied, and just trying to guess what the right values are. And yes, it's been an awful lot of guesswork, an awful lot of crashes into brick walls as a result. So yes, there's a red card there. I'm being sent off. It's a good time.
Want to go for a few minutes break for the next talk, but I think that was a really interesting talk, very good demonstration of what to do with the pie. So thank you very much.
Okay.